Welcome back to ECE 220. This Saturday is a deadline. It's an off Saturday, so you won't have a game to interfere with. There's a bye week. You can get your pre-labs submitted on Saturday. That's for 4 of the 5 sections of the class. That's Group A, and there is an assignment folder that you can submit those into, and I believe the TAs are wanting you to put all of your material, whatever that consists of, into one PDF file. So try to conform to that process, and we'll see how it goes. Next week is when Group A begins Lab 1 based on your pre-lab, and that will be Tuesday through Friday at your assigned day, depending on your section. Homework 4 is dealing with Chapter 4 material, and in particular node voltage analysis. Today we're going into a dual universe. We're going into the dual concept, which is mesh current analysis, and that will be Unit 5. We're starting a new unit, but that's still in the same chapter. We're still in Chapter 4. And while all of that is going on, you're going to have an exam a week from tomorrow. That's Thursday in this room, and it will essentially be, I'll give you an hour to complete that exam, and you'll try to sit. Wow, these are staggered, so I'm not sure how we will do this. We might start on an end that does have them in stacked versions, but I don't know what we'll do with the center seating. We'll figure that out. We have a week to do that. Since we are going into a dual universe to learn about mesh current analysis, which is the dual of node voltage analysis, we'll refresh our memory on some of the terminology, or actually go into that table 4.1, and the accompanying figure, and remind ourselves of some of these terms that we really didn't need to worry too much about with node voltage analysis. And today one of the big themes is making the distinction between branch currents and mesh currents. Sometimes they're the same, but how do I want to say this? Sometimes I1 equals IA, but I2 might not be equal to IA. So branch currents and mesh currents are different concepts, but they can, depending on how they are defined, be consistent or equivalent. We'll then introduce mesh current analysis, and we'll look at one example where we have 2 mesh currents. And then we will look at one that has the presence of a current source or that current source component is only associated with one mesh, and in that sense it eliminates a mesh current. Let's now return to table 4.1, which is on the left, and the accompanying circuit that is using these definitions, or these definitions are then showing via example what's going on in the circuit, which is figure 4.3. Here what we want to do is look at the middle terms, and in particular, let me make sure I get the colors correct, dealing with a path. So now, and correct me when I misspeak, but we're going to have paths, we're going to have loops, we're going to have meshes, and we're trying to be precise in how those terms are used. A path is really just starting at one node and going to another node without really passing through or passing over yourself. So that could be considered a path. It doesn't have to start and stop at the same location. That's the path, a path. And there's multiple paths, obviously, in this circuit. A branch is just what connects 2 nodes. A branch could then go through a given circuit element. That's a branch. That connects two nodes. Then they make the distinction between a branch and an essential branch. A branch could connect these two nodes, D and E. But D is not an essential node. An essential branch connects essential nodes. Do you get the distinction between a branch and an essential branch? An essential branch could be connecting those two essential nodes, which are C and E. There are other essential branches in this circuit, but I'm just illustrating one. And they illustrate another one. They go through V1, the voltage source, through R1 in their third column. That's an essential branch. It connects two essential nodes. A branch just connects two nodes. Those nodes do not have to be essential. Now, the more important pieces of this left column of terms involve the next two, a loop and a mesh. The loop can be a big, maybe, since the loop's on top, think of it as maybe a bigger thing than a mesh can be. A loop is now going to be a path that begins and ends at the same node. But that loop could go anywhere it wants, essentially, through that network, as long as it starts and stops at the same node. So a loop is a path whose last node is the same as the starting node. That is now distinguished from a mesh. A mesh is a loop that does not enclose any other loops. Do you see that I could draw a loop in the top window that involves V1, R1, R5, R3, and R2? I could draw another loop that involved V2, R2, R3, R6, and R4. And my earlier loop, it didn't care. It just went ahead and went around all of those two loops. A mesh can't cross over into another mesh. Yes?
So for example, what is the example in the table start with V1 V2?
So now the question was, why is my example different from what's in the table?
Start from V1 but ends with V2.
So now a loop can start, I can't read that. Is that V1 and V2? So it's basically, so it's starting this loop in the table. If you look over to the third column, it's starting at V1, but then it's really my same loop. It goes through R1, R5, R6, R4, and it goes through V2. So it ends up at the base of V1. So it's starting and stopping at the same place, even though the notation doesn't look like it's coming back and reaching its tail. It is. So it's starting at V1 and going all the way around through V2 up to the head of V2, which is the tail of V1. Does that help answer your question? That's a loop. The mesh is distinct from that. A mesh is now, here's another mesh. Here's another mesh. Here's another mesh. Think of meshes like panes in a window. That's how to sort of think of a mesh. Pardon? And a loop, you could include multiple panes in your loop. It would be a pain, but you could do that. Okay? Sorry. Let's move on. Let's determine now how we can apply that in mesh current analysis. And because we're dealing with windows and panes of the windows, that means mesh analysis really only works for planar surfaces, or planar networks, which are networks that you can put on a plane without any crossing lines or wires. So this works for planar circuits. Node voltage analysis works for planar and non-planar, but mesh current analysis only works for planar circuits. Let's now look at the distinction between branch currents and mesh currents. Branch currents are what they are named as. They're currents associated with different branches. We could call this current I1. Is I1 going through V sub S? Yes, so I1 is here as well. Here's, let's say, I2. That's going through the branch that involves R2. Branches connect nodes. R3, here is a third branch current going through the R3 branch. I sub 4 is the current going through the R4 branch. I sub 5, and don't get hung up on which direction this goes. You could put it a different direction. It doesn't really matter. You just have to live with how you define it. I'm going to go from left to right and call I5 the branch current through R5, that R5 branch. And we then have a branch current, I sub 6. And we could relate all of those using KCL if we wanted to. But branch currents are simply currents going through different branches. So how many branch currents do we have in this illustrating circuit? It's not hard. 6, right? So we have 6 branch currents, and those were I1 through I sub 6. The mesh currents, in contrast, are now associated with these meshes that we can identify in this circuit. Here we see 3 meshes. Let's say here is the A mesh, and we'll label that as I sub A to be the mesh current I sub A. Here is mesh current I sub B, and here is mesh current I sub C. And I color-coded this wrong, didn't I? But anyway, we're kind of contrasting. There's 3 of these, I sub A through I sub C. Are we clear now on the distinction between branch currents and mesh currents? And do you see that I sub 5, to create that or to define that in terms of mesh currents, that will require 2 mesh currents to create that? How would I write I sub 5 in terms of mesh currents? What is I sub 5 in terms of these mesh currents? Is it I sub C? Is it I sub B? Is it minus I sub B? Is it I sub A? No. I sub 5 is what? Well, I like to think of what's going in the same direction as I sub 5. Which mesh current? That's I sub C, but I sub B is going against it. So the algebraic sum of I sub c and I sub b form that branch current I sub 5. I sub 5 is I sub c minus I sub b. Does that seem logical? So now the mesh currents, don't get too hung up on how they are related to the branch currents just yet, but we kind of need to know this relationship. But the mesh currents are really there to try to simplify our analysis. The mesh currents are dual to the node voltages. Remember how we labeled essential nodes relative to a reference node to get these node voltages? Now we're just drawing in, instead of having to work this circuit with 6 unknowns, now we can solve it with just 3 unknown mesh currents. And then we'll back out the branch currents if we need it. So that's the idea. Let's just solve this circuit as cleanly as we can. And in this case, we can solve it with just defining 3 unknown mesh currents. And if somebody at the end says, well, what's the power absorbed by R sub 6? Well, that's easy because it just involves I sub c. But if you now said, what's the power of R sub 3, then you would have to figure out, well, what's I sub 3? Because the power would be R3 I sub 3 squared. And in this case, what is I sub 3 in terms of mesh currents? I sub 3 is I sub a, which is going in the same direction, so that's kind of helping I sub 3, and I sub c is hurting or taking away from I sub 3. I sub 3 is I sub a minus I sub c. That's going to be used now, that thought process, when we write or apply KVL in each of these meshes. We're going to now write KVL just like we wrote KCL in node voltage analysis. Now we want to write KVL equations associated with each of these meshes. Mesh A, let's start in the lower left-hand corner. And if we now sum drops, the first thing we see is a rise, so that's a negative drop. It's minus V sub S. Then we have plus R1 I sub A. That's the drop from left to right across R1. Then we want to know what's the drop as I go in voltage as I go down through R sub 2 in terms of mesh currents and R sub 2. It's the resistance, it's Ohm's law. R sub 2 times the net current down through R sub 2. And the net current down through R sub 2 in terms of the mesh currents, I sub A minus I sub B. Then we drop down and we go, what's the voltage dropped across R sub 3? R3 times the current from top to bottom, IA minus IC. That's KVL for mesh A. Let's write that down. KVL around mesh A is then the drop, which is a negative drop, minus V sub S plus R1 I sub A plus R sub 2 I sub A minus I sub B plus R sub 3 times I sub A minus I sub C, and then we're back where we started. That's KVL in terms of the mesh currents. What about KVL around mesh B? Let's start again in the lower left-hand corner of mesh B. Now we want to know what's the voltage dropped across R2 when we go from bottom to top, and that's going to be a positive. How do we drop voltage across R2 in terms of our mesh currents and R2 and Ohm's law? Do you see now we're really going against I2 in a sense? We want to go, what's the net current going up through R2? That's IB minus IA. And we'll multiply that by the resistor R sub 2. Then we work our way around and we go, what's the voltage drop across R4 in terms of mesh currents? That one only involves one mesh current, doesn't it? That one's the easy one, so to speak. That's R4IB. And then we want to drop voltage from right to left across R sub 5. R sub 5 times the net current from right to left, and that's IB minus IC. What did I just say? Let me go back to my diagram on my paper, and I now went through R2 first, and that was IB minus I sub A, drop going up, plus R sub 4 I sub B, plus R sub 5, and now we want to drop from right to left. That is now I sub B minus I sub C. Kind of an accounting. I saw all these review sessions on the door for accounting, so now I'm thinking accounting for different exams. But we can do some accounting here, some bookkeeping. Look at what happened in mesh A. I sub A was always positive, and the neighboring currents were negative that come into that formula. And that is only going to be true if we keep all of our mesh currents defined clockwise, or we look in a mirror and now we make them all counterclockwise, but don't mix them. If you mix them, then this thought process will go out the window, out of mesh. It'll create a mess in our mesh analysis. What about B? What's I sub B? Do you see how it comes in positively? And when we have an adjoining or an adjacent mesh, that mesh current comes in negatively. Let's look at C. Mesh C starting in the lower left, R sub 3 times IC minus IA plus R sub 5 times IC minus IB plus R6 times I sub C, we're back where we started, equaling 0.
So are we going to have examples where our directions of our mesh currents will be going in the same? Like that they're, one's going clockwise, the other's counterclockwise, and then we'll be adding them?
Did everybody hear that question that was being raised? I'm going to pretend I didn't. No, I'll answer it. The question, I think, was consistent with what I was talking about with a messy mesh. If you now start saying, oh, I want I sub A to be clockwise, I want I sub B to be counterclockwise, I want I sub C, I don't know, flip a coin, counterclockwise, then this bookkeeping strategy that I just mentioned is out the window, is out the mesh. Because then we sometimes will be combining our mesh currents, I sub A plus I sub B, to get the current going net down. So if you want to kind of have this ability to check your work with some accounting, you make all of your mesh currents in the same direction. And typically I just do clockwise. But if you want to do them counterclockwise, just make them all counterclockwise. Mixing them, then no more accounting strategies. If you're comfortable with this, then you could actually, by inspection, put that mesh information into a matrix structure. What? So here's how you could do it. The first row is going to be mesh A, the second row is mesh B, and the third row is mesh C. And we're trying to find these unknown mesh currents, I sub A, I sub B, and I sub C. Currents times what give us voltage? This is now going to be an impedance matrix that's 3 by 3 in this problem. We have 3 mesh equations, and we have the 3 unknown meshes to solve for. What's going to be in the right-hand side, resistance times current gives us voltage, so we'll be seeing voltages in the right-hand matrix. You could now fill in this matrix, which has 9 elements in the 3 by 3 matrix, by simply rewriting this A equation and combining or identifying the coefficients for each of the mesh currents. I sub A, what are its coefficients? So it's R1 plus R2 plus R3. Hey, wait a minute. If we go back and if we look at this by inspection, what resistors did I sub A touch? R1, R2, R3 on its little adventure. That goes in the 1-1 entry. That's the 1-1, that's the diagonal entry associated with I sub A. Then if we look at this and we say, oh, we have a minus R2 I sub B. Let me fill in the first one first. So here was R1 plus R2 plus R sub 3. Those were the resistors that I sub A touched in mesh A. I sub B has a coefficient minus R sub 2, and I sub C has a coefficient minus R sub 3. And the voltage we put on the other side of the equality sign, we're adding V sub S to both sides of this equation, and we have V sub S over there. Now, how could we write that down by inspection of the circuit? Here's how we did it, basically by just comparing terms in that first expression or first equation. That you can do by looking at or combining the appropriate coefficients. But here, by inspection, you say, okay, I'm doing the first mesh, mesh A, and I say, is there anything on the right-hand side? Do I have any sources? Yes, in that mesh I have one source. If I increased that source voltage, would that serve to increase I sub A or suppress it or make it smaller? If I cranked up V sub S, what would I sub A want to do? What would the mesh current do? Up or down? Would it increase or decrease? It increases, doesn't it? So we put on the right-hand side of that matrix expression, we have a voltage. We put it over here with a plus sign because it was actually helping to increase I sub A. And it came in as a plus by just copying it down in the right way from that equation. That's how we would account for the sources. the resistors in the resistor matrix. What resistors touch I sub A? Oh, R1, R2, R3. Boom, their sum goes in the diagonal entry in the matrix. And I sub A is the first element in our unknown vector, so it goes in the 1, 1 entry of our diagonal matrix. Is R2 shared with any meshes? R2 is shared. We're writing mesh A, it's shared with mesh B, so it comes in with a negative. R2 is going to be a negative in the second column of the first row. What about R3? Oh, it's shared with mesh C. It comes in with a negative relative to I sub C. All right, now I've given you the formula to do this by inspection. How do we write the second row of our matrix equation by inspection of this circuit? What goes in the 2, 2 entry of our resistor matrix? We just add up all the resistors that touch I sub B. R2, R4, R5. So we do that immediately. We come down here and we say, oh, my 2, 2 entry is R2 plus R4 plus R5. Then I go back and I say, okay, is there any resistor or resistors shared between mesh B and mesh A? R2, that comes in with a negative. And that was in the I sub A entry. What about any resistors shared with mesh B and mesh C? R5, and that comes in with a negative. Were there any sources that helped or hindered I sub B in mesh B? No direct source in that mesh. The right-hand side is 0. And you can get exactly that same equation if you simply collected consistent coefficients associated with I sub B, I sub A, and I sub C in that second equation. By inspection, how do we write the third and final row of that matrix expression? What's in my diagonal entry? All the resistors touched by I sub C. R3, R5, R6. Off diagonals, oh, in the first column of that third row, I sub A, yes, it shares R sub 3. R sub 3 is going to come in with a negative. Oh, R sub 5 is shared between B and C. In the B column, which is the second column, that's going to come in with a negative. So this now becomes, whatever it was, we had R3 plus R5 plus R sub 6 touching I sub C. Shared between I sub C and I sub A was minus R sub 3, and shared between mesh B and mesh C was R sub 5. It comes in with a negative, and there was no source directly in that mesh helping or hindering the I sub C current, so we have a source of 0 on the right-hand side. This is easy to build when we have no dependent sources. And what do you see in that resistor matrix? Do you see any nice structure? And maybe that's a definition of nice. But if you look across the diagonal, do you see that it's symmetric? It's symmetric because we do not have any dependent sources. Here's the current matrix, and here's the voltage matrix. So it's Ri is equal to V. That's Ohm's law in matrix form. This is symmetric, so we had no dependent sources. And that allowed this to be performed pretty easily by inspection. And this matrix was symmetric because of no dependent sources. When we have dependent sources, then it kind of clouds things. It makes things a little more messy. Let's do an example. Another example. In this example, the goal is to find all of the branch currents. How many branch currents do I have? You could define 5. Well, it would be every element, but some of those are the same, aren't they? The current through the 1 volt voltage source is the same branch current as the one through the horizontal 3 ohm. The vertical 3 ohm has its own branch current, and then there's a branch current that's the same between the 6 ohm and the 3 volt voltage source. There's 3 branch currents. How many mesh currents do we have? 2. We have 2 meshes that we can identify. So let's just put those in. Let's now say here is I sub A and here is I sub B, and I made those go clockwise, both of them clockwise, just to help me. And what I'm going to do now is I'm going to write KVL equations with these mesh currents, and then I will use those mesh currents to determine what my branch currents are. So I'm asked for branch currents, but I don't want to find those directly. I'm going to do that indirectly by first solving this circuit using mesh analysis, writing KVL equations, and these mesh currents I sub A and I sub B. What's the KVL equation for mesh A? That should just be almost very straightforward, is it not? We start at the lower left and we say, oh, minus 1 plus 3 times I sub A plus 3 times I sub A minus I sub B. We're done with KVL for mesh A. This is now minus 1 plus 3 times I sub A plus 3 times I sub A plus, minus I sub B is equal to 0. That's KVL for mesh A. This you should get very comfortable writing. What about mesh B, KVL? Starting in the lower left. Or if you say, I want to get started on a good note, you say, let me start in the lower left, just to be consistent. But you could start with the 6 ohm, and then it would be 6 times I sub B. You wouldn't have to worry about a shared current or mesh currents messing you up. But starting in the lower left of mesh B, we have 3, and now I want the drop going from bottom to top. That's now times I sub B minus I sub A, plus 6 I sub B plus 3 equals 0. So KVL for B is now 3 times I sub B minus I sub A plus 6 I sub B plus 3 is equal to 0. That's basically step 2 of this mesh current analysis. We identified the mesh currents. That was step 1. Step 2 is write the equations that govern those mesh currents. Now we need to solve this. This is 2 equations and 2 unknowns. the two unknown mesh currents, I sub A and I sub B. And we can solve this however you want to do it. Let's just do it by basically rewriting equation A in terms of, let's solve it for I sub A. Now equation A we can rewrite as 6I sub A minus 3I sub B is equal to 1. And that says then that I sub A, if we move the 3I sub B over to the other side and divide by 6, we end up with 1/2 I sub B plus 1/6. That's I sub A. Now if we use that in B eventually, equation B is going to be minus 3I sub A plus 9I sub B is equal to minus 3. Now let's use that to get rid of I sub A, and we now have minus 3 times 1/2 I sub B plus 1/6, that's I sub A, plus 9 I sub B is equal to minus 3. And now we have one equation in the one unknown I sub B. We have minus 3/2 I sub B minus 1/2, and I'm going to rewrite that 9 as 18 over 2 since I have 2's everywhere. So this is now plus 18 over 2 I sub B is equal to, I don't know why, I'm going to just go ahead and keep the 3. But I can now multiply everything by 2 and eventually combine, but let me just say I have minus 3 I sub B minus 1 plus 18 I sub B is equal to minus 6. Or 15 I sub B is equal to minus 5. Or I sub B is minus 1/3 amp. And I can now use that up here to find I sub A. I sub A is now 1/2 times minus 1/3 plus 1/6. Huh? It is what it is. 0. That mesh current is 0. Meaning, we now, if we plug that information in down here, we now have learned that this current, I sub B, is minus 1/3, and this mesh current, I sub A, is 0. They're my 3 branch currents, which is what I was trying to find. That was what was asked of me to begin the problem. How do I find I1, I2, and I3? I've already solved for the mesh currents. I should be able to back out those branch currents. What's I sub 1? Can you write I sub 1 in terms of the mesh currents? It's just I sub A, isn't it? There's no other shared mesh current with that I sub 1. This is I sub A, which we computed to be 0. That branch current is 0. What's the voltage dropped across that horizontal 3 ohm resistor? 0. There's no current flowing through that resistor. So at the top of that vertical 3 ohm better be the same as what's on the left of that horizontal 3 ohm, 1 volt. We'll see if we can check that. But there should be that same 1 volt source across that vertical 3 ohm resistor. Let's wait. Be patient. Let's wait. Let's see. What's I sub 2? In terms of mesh currents. This is why we tried to kind of get our head around how to relate mesh currents and branch currents. What's I sub 2? I sub A minus I sub B. That's the net current down is I sub A minus I sub B. And that now is a minus 1/3, or I sub 2 is 1/3. We have 1/3 amps going vertical from top to bottom. What about I sub 3? What's I sub 3? Pardon? That's just I sub B. And I sub 3 is then minus 1/3 amp. So can we do any kind of checking? Could we say, what is this voltage here? Did I convince you what that should be? What's the voltage dropped across our horizontal 3 ohm resistor? The horizontal 3 ohm is Ohm's law, 3 I sub 1. 0. So now if I looked at the left node of the horizontal 3 ohm and I looked at the right node, what's the voltage? What's the voltage difference across that 3 ohm horizontal? What's this voltage? What did you just tell me that voltage was? 0. Can you do KVL? Minus 1 plus 0 plus V. Do you see what V has to be? V better be 0. Can we check that? Well, that's now the 3 vertical times I sub 2. But 3, and what was I sub 2? Right? We just checked our work. We good? What about this voltage? Let's call it V sub 6. Do you see how you can check your own work now? You can back all of this stuff out and try to convince yourself of what you would measure in the lab. What's V sub 6? Well, I could do KVL now. I have 2 voltages on either side of that. If I wanted to, I could say minus V plus V sub 6 plus 3 is equal to 0. And minus V is minus 1. So this is now V sub 6, is equal to minus 3 plus V minus 2 volts. What's V sub 6 from Ohm's law? I pulled a muscle on the last dance, so we'll just be okay with this one. But it checks, right? Thankfully, I didn't quite pull anything, but do you get the idea? Now, what happens here? What happens here? One more. We've got time. We're still in the last seconds of the game. We still have some time to learn a little something or to score. Let's score. Yeah, it's always good to score. How many meshes? I'm losing my audience. They're going to the concession stand. They'll be right back. Intermission. Ooh, good thought. We'll be back tomorrow. Okay, how many meshes? 2. I sub A and I sub B. Let's just step back. Do I actually have to solve for I sub B? If somebody tells me what that current source is, I know what I sub B is. I sub B is the negative of that current source. I just have to solve for one unknown mesh in this circuit. Isn't that a win? We'll leave on that note, but we'll pick up there next time.